Okay, next one we have is a feature called IGP synchronization. Now, as I mentioned before, we can run into problems with traffic being black holed in the MPLS core if LDP and IGP is not on a one-to-one basis. Now, what this really comes from is the process of how LDP figures out what is going to be the specific label that we're going to use for a specific destination. So how do we correlate the routing table, the label information base, and then combine these together to form the label forwarding information base, basically the active labels that we're using towards those particular destinations. So let's say, for example, that we are running LDP, but we're only running it on a portion of the network. Let's say we're running it just between routers 1, 2, and 3. And what we're ultimately trying to do is to transit traffic between router 5 and router 7. So router 5 is an L3 VPN customer, or in other words, it is the customer edge router. Router 1 is the provider edge. Then likewise, router 7 is a CE, router 3 is a PE. So we have some sort of routing exchange between these two, which is our PE to CE routing protocol. And then between router 1 and router 3, we're exchanging the updates, the routing updates of the customers by running VPN version 4 BGP. Now, as we'll see once we start to get into the details of this, one of the big attributes that we need to be aware of is what is the next hop value for the BGP route that you're advertising between the PE neighbors. And again, as we saw previously, this next hop value is going to have to be the loopback typically. So what would happen is that 7 advertises a route to 3, 3 advertises it into VPN v4 BGP, and it says the next hop is my loopback. It's 3333. Now, from router 1's point of view, assuming that our IGP routing goes 1 to 2 to 3, and 1 to 2 to 3 is also where we have LDP enabled, then it means we should be able to use a labeled path in order to reach that destination. But if for some reason IGP is not following that path, let's say that the traffic routes from router 1 to XR1 to XR2 down this way and then over to router 3, and if there is not LDP here, it means ultimately when traffic comes in from router 5 trying to go to router 7, router 1 is going to send the packet this way as native IP as opposed to an MPLS packet. And the problem would be that this P router, or essentially the core of MPLS, is not going to know about that final destination. So again, we will revisit this problem once we have L3 VPN built, and we'll see how this can actually affect the end result of black holing the traffic. But the point in this scope is that there is a mechanism to try to stop this. It's called IGP synchronization with LDP, and what it is designed to do is to say if for some reason I fail to form an LDP adjacency between the two neighbors, I'm going to try to avoid that neighbor as an IGP path towards a particular destination. So let's say, for example, now from router 1's point of view, that we're trying to figure out how do we route to the loopback of 3. So if we look at from 1 currently, and we, from 1, look at show IP route for 3333, it says I have 2 equal cost paths. I have one that's going out gig 1 112, which is going this direction, and I have one going out gig 1.12, which is going this direction. Okay, if we were to do a trace and we go to 3333, we should see that we're following a labeled path. So regardless of whether we're going to router 2 or to XR2, we have labels available in both directions. So if we're tunneling over MPLS, it should be fine either direction. Okay, but now let's say there's a problem in LDP. So maybe on router 2, we configure an access list that breaks LDP. So let's say IP access list break LDP is going to be extended. And let's say we're going to deny TCP any equal to 646, or deny TCP any equal to 646 any, and permit IP any. Okay, then on interface gig 1.12, we have IP access group break LDP in. Okay, now eventually, once the keep alive expires between the neighbors, the session is going to get torn down because we can't directly route TCP between router 1 and router 2. Now to speed this up, let's go ahead and just clear the session. Let's say clear IP or clear MPLS LDP neighbor 1111. Okay, same thing from router 1. So the session goes down. If we show MPLS LDP neighbor 2222 detail, we should see there's no neighbor established. But from an IGP routing point of view, when we look at 3333, notice that this hasn't changed what's going on in underlying ISIS routing, because they're two separate processes. IGP routing and LDP label switching aren't directly connected. So the issue now would be if I go to label switch traffic over router 2, so we do a trace route to 3, we see that one of the paths is unlabeled and the other path is labeled. So for any packets that go this direction, router 2 is going to drop them, because router 2 won't know about the final destinations that are reachable behind router 3. And again, this is where LDP synchronization comes in. So synchronization says that we're going to protect the link to say if where LDP is broken for some reason, we want IGP to reroute around this. So specifically the way that we do this is, let's go ahead and bring the IGP link down between router 1 and router 2. So we'll shut this down temporarily. On both sides, gig 1.12, shut this down. Then under router ISIS, we're going to say MPLS LDP synchronization. Okay, same thing on router 1. Router ISIS 1, MPLS LDP synchronization. Okay, then on gig 1.12, we'll say no shut. On gig 1.12, no IP access group, break LDP in, and then no shut. Okay, so now the interface should come up, ISIS adjacency should form, and then also our LDP adjacency should form. Okay, ISIS is up now, LDP is up. Okay, next from router 1's point of view, we look at the show MPLS LDP neighbor 2222 detail. And what we're looking for is that and it's actually not under this output, it is under show MPLS LDP IGP sync. And it says that for gig 1.12, synchronization is enabled and synchronization has been achieved. Okay, notice on the other interfaces it says synchronization is not achieved. This is because they don't have it enabled on the other end. So this is typically a feature that you run on every single device in the core, that you run LDP autoconfig to enable LDP everywhere, and then you run LDP IGP synchronization to prevent against these problems. Now on the current interface that is synchronized, the next step is that there's a problem with routing. So we go to router 2, or not a problem with routing, there's a problem with LDP. So we say that we have this access list that now breaks the LDP communication. From router 1's point of view, if we show IP route 43333, we see that it's currently reachable through both paths. If we trace to 3333, one of them is currently labeled, or actually both of them are currently labeled, until we lose the TCP session that is between the neighbors. Okay, so next let's say TCP breaks. We clear MPLS LDP neighbor 2222, and the neighbor can't come back because there's that access list that is blocking the communication. Okay, if we now look at the show MPLS LDP neighbor, or show MPLS LDP IGP sync, it says on this interface, synchronization is not achieved. The end result now, when we show IP route for ISIS, is that 3333 is no longer reachable out that directly connected link between router 1 and router 2. Or in other words, when we go to do our trace route, the IGP routing is going to avoid the link that is directly between router 1 and router 2, because it says that LDP is down, and the end result is that if I actually route packets out there, I know that they're going to get black holed. So what we're going to do instead is to try to reroute the packets through any other available link that does have LDP running. And again, you would typically run this on all of the interfaces, or all of the routing processes globally. So like in the case of XR2, we would say under router ISIS1, address family IPv4 unicast, MPLS LDP, or no, where is it? It is under MPLS, let's see, is it under MPLS LDP? IGP synchronization. So how do we, let's see, how do we enable this globally? Okay, so in iOS XR, let's go to the main XR documentation. Let's go down under configuration guides under ASR 9000. This would be under MPLS configuration. And then under multi-protocol label distribution protocol. Okay, let's search for sync. IGP synchronization, configuring LDP IGP synchronization ISIS. It's under, why did it not show it there? Oh, it's under the interface level is why. Okay, so when we look at the do show run router ISIS, we would say this at the port level. So we would say on all of these interfaces, and let's just say this one here. So router ISIS 1, under the link, under the address family, MPLS, LDP, sync. And then also on, let's see, what's the interface between us and router 1, which is 1112. Is that what I said? 1112. Okay, so we have synchronization on. Let's say show config, and then commit the config. From router 1's point of view, when we show MPLS, LDP, IGP sync, we should see now that that interface is in sync, synchronization is achieved, and the peer is reachable. So again, what it's basically saying is that now if LDP goes down, we're going to change ISIS to try to reroute around the failure. Now, the way that it specifically did this, if we look at the show ISIS database detail, and what we would be looking for here is the link state packet that router 1 generated, talking about the link between 1 and 2. So specifically the one that is representing gig 1.12. And we should see this towards the top, router 1's own link state packet. And notice what happened. It gave it the maximum metric value. So basically what it's saying is that as long as there's another alternate path available, I'm going to make this path that's broken less preferred by just raising whatever the metric is. And the same is true of OSPF. So if OSPF was running here, under the router LSA, it would set the maximum metric, which is 65,000, to the link between them, or to the adjacency between them, basically, and it forces OSPF to reroute around another interface. But again, this only is going to work if there is an alternate IGP path. So for example, like in this case, when we look at what's router 1's route to router 2's loopback directly, this is not going to be impacted by this if we show IP route for 2222, if that's the only path to get there. So what I mean by this is that if we were to go to the other interfaces, which are, from router 1's point of view, they're gig 1.111 and 112. And if we were to shut these interfaces down, it says, well, now there's only one possible path, it's that direction. I'm going to have to use that link. So specifically, let's say on interface gig 1.111 is shut down. Interface gig 1.112 is shut down. If we now show IP route for 2222, it says, well, there's only one way to get there. Actually, there's another link. There's only one way to get there, and even though the metric is large, it's still a valid metric. It's not an infinite metric, it's just a very large value. So in this case, it wouldn't fix the problem if the only possible path loses synchronization between IGP and LDP, but they're assuming that you probably have redundancy in terms of link level redundancy within the core. So from 1 to router 3, as long as you could route maybe that way, or this way, or this way, or basically any other possible path, you would always prefer to use a labeled path as opposed to an unlabeled path. So again, specifically within the case of iOS XR, this goes under the address family, and then MPLS LDP synchronization under the port. Within the scope of ISIS, within the scope of OSPF, it goes under OSPF under the area. Okay, so either you could say all interfaces are running synchronization, or just this area, and then those particular links. But the final verification for this would be the show MPLS LDP IGP sync, and it should say that synchronization is enabled and that synchronization is achieved. Okay, there's a question, what happens when LDP crashes somehow? When synchronization is enabled and no interface running LDP, can we lose access to that router? So that's kind of an interesting question that, well, what happens if there's no labeled path to get there? You would still use the route, it's just that it would increase the metric value. So you shouldn't lose access to the router, like you can't route through it all anymore. It's just that you would be using an unlabeled path as a last resort path, which is basically what we have in this case. And when we look at show IP route for 3333, right now there's only one possible way to get there, which is through router 2, even though this is an unlabeled path. So as long as one additional path comes up, like on gig 1, 111, we re-enable that interface, we should form ISIS adjacency, then we should form LDP adjacency. Once those are up, we should see that the routing table is going to change to use gig 1.111 as opposed to 1.12, which it is now. So let's show ISIS neighbors. Let's ping 10.1.11.11. Okay, this says we have an LDP adjacency with them. And why do we not have an ISIS adjacency with them? Mentioned, just to summarize, synchronization raises the metric of the route to infinity in case LDP is lost on the link, correct. So the idea is that you want to reroute around that, and the way that it automates it is just by raising the cost to say try to find an alternate path as opposed to going through the non-labeled path. So in this case here, I should be reestablishing adjacency to router 1. So from 1, let's show ISIS neighbors. Let me try shutting down the interface. Now, sometimes you'll find with the virtualization with XRV that you'll need to flap a link in order to get the feature to reestablish like adjacency. So even though they're logical subinterfaces, you may want to, if you have a problem and you're not sure if it's configuration related or software related, just shut the port down, no shut it, and then recommit. And it says we have an LDP adjacency. Why do we not have ISIS adjacency though? Show CLNS interface gig 1.111. Show ISIS neighbors. Clear ISIS neighbor star, or clear CLNS. Okay, so this problem is unrelated. For some reason, router 1 and XR1 stopped forming adjacency. What I can also do is on XR1, if we go to global config and say commit replace, again, this is deleting all of the config. Then if I go back to exec mode and say roll back my config last one change, what this is basically doing is stopping all routing processes and then restarting them. Sometimes you'll see, because we're adding features and constantly removing them, that, let's see, hopefully did that form. Okay, it says ISIS startup, show ISIS neighbors. No, it didn't fix the problem. Okay, but that's unrelated. Let's leave that alone for now. There was another question. I'm not sure I get it. So IGP synchronization is used when there is no label path. Could you please run through the concept again? Okay, so the problem is that we're trying to get traffic to go from router 5 to router 7. Okay, these are customer edge routers. They're part of layer 3 VPN, which means that the devices in the middle, they don't know the routes between them. So from router 2's point of view, who is in the core, if we go to router 2 and say ping to 7, it's not going to get there because it doesn't have the route. But the solution to that is to tunnel the traffic over it. So we're going to use an LDP-based tunnel by running IGP plus LDP on all of the interfaces in the core. Okay, then when router 2 gets the packet, as long as it has a label number, we can label switch the traffic in gig 112, out gig 123, and then router 3 knows where the final IP destination is. So as long as the label switch path is working, router 2 can transport the packets. Okay, then the issue is that for some reason LDP adjacency fails. Like the LDP process crashes, someone misconfigures it on the interface, there's an access list that drops it, whatever. For some reason, router 1 and router 2 stop forming LDP adjacency. Now, from an IP routing point of view, though, by default, this doesn't change your underlying IGP path. So when router 1 does a trace route to router 3, if the regular IP routing path goes through router 2, it means traffic from 5 to 7 would be blackholed when it gets to router 2. Because the problem is 2 doesn't know the final destination. It only knows the egress PE router, which is router 3 out of the core. So the solution for this is that if for some reason LDP breaks, try to reroute automatically around the node that had the break. So what happens is that when we run synchronization, we say, okay, we know we lost the LDP adjacency, try to not use that link to get to the destination. So we can reroute this way, we can reroute that way. Doesn't really matter as long as we're not going through router 2. And the way that the process does this is to automatically raise the metric of the link to something that is less preferred. So again, on router 1, when we looked at the show ISIS database detail, and we looked at the link state packet, it advertising its adjacency to router 2. It's setting this to be an infinite metric. Well, not technically infinite, it's just a very high metric. So then if I say I have a path to router 3 here, and I have a path to router 3 over the infinite metric path, I'm going to choose the one that has the lower cost. So we tried to reroute the IGP path, which implicitly means that we're rerouting the LDP path. Because the key is when you look at the show IP route, and you look at the show MPLS LDP bindings, you take the combination of these two together, that's what forms the label forwarding information base. So let's say, for example, we're looking at the label that goes between router 1 and XR3. Okay, we're trying to figure out from router 1's point of view, how does it actually choose what interface we're going to use to get to that labeled destination? So first off, router 1 says, well, what's my IGP route? How do I get to 13, 13, 13, 13? Okay, I have a route that goes through router 2. Okay, next it says, well, do I have an LDP adjacency with them? Show MPLS LDP neighbors, pipe include 10.1.2.2. I don't. So this means even if that interface is running labeling, for some reason I don't have a binding that includes that next hop value, it means that will be an unlabeled path. So if we trace to 13, 13, 13, 13, LDP is broken. Okay, now we have the fix. The fix is that router 2 stops dropping the LDP packets. And specifically here, this was just an access list. So we configure the access list. We say don't break LDP. So 1 and 2 should reform their LDP adjacency. If we now show IP route for 13.13.13, it says we go to 10.1.2.2. We now show MPLS LDP neighbors for 10.1.2.2. Now we do have a neighbor that includes, well, actually it doesn't have to be that, that address. We would say show MPLS LDP neighbor pipe include 10.1.2.2. And there is a neighbor that is running LDP on that interface. So this means we look at, well, what's the label number that came in from them? Since I'm using that as the best path for IGP, that should be the specific label number that I'm now using. So if we look at the show MPLS LDP bindings for 13.13.13.13, and the mask is /32, it says I have two possible labels. I have label 43 through router 2, and I have label 16,004 through XR1. But if we look at, well, what was that next hop value that the IGP route was using? The next hop value was for the neighbor that was 2222. It means the label number that we're going to use is 43. So when we show MPLS forwarding table to 13.13.13.13, we should be using label number 43. So really the key point here is that you can learn multiple labels to the destination, but the only one that is being used is the agreement between IGP and LDP. So the way to change the label is to change what is the IGP route. So likewise, if I was to say, let's statically reroute around this. Let's say IP route 13.13.13.13/32 is now reachable via 10.1.11.11. If we now look at the MPLS forwarding table, now the label changes, because if I change what the IGP path is, it means I change what label I'm pulling out of the label information base in order to go to the LFIB. So IGP synchronization is doing the same thing, it's just an automated process. Instead of manually changing the static route, it's automatically changing the cost of the IGP route to repoint IGP to a different interface. So again, in most typical designs, you would run both IGP autoconfig and IGP synchronization for LDP, and then for any interface you enable OSPF on or ISIS on, you automatically enable LDP, and if for some reason LDP breaks, then IGP will try to reroute around to another label path, which means that we're not going to black hole traffic over the MPLS core.